All right, so as you kind of saw from the intro, we get into the weeds a little bit in this class of the logic, and we are going to be very, very particular about how things are written. So you can't be lazy, not lazy, but you can't really, you can't be sloppy about when you write something and when you say something, because again, when we write something or we say something, we have to be very accurate in terms of mathematics and mathematical logic. So we're going to look at compound statements here, and what I mean by compound statements is we saw simple statements earlier. You know, statements like today is Monday, the horse is gray, all ferrets smell bad, I am your father. Those kinds of simple statements. Those are what we call simple statements. Okay, those are the things we saw in the introduction. Some of them have quantifiers. All ferrets smell bad. Those have quantifiers. But they're all statements that can be proven true or false. And we're pretty short to the point statements. Now, what those simple statements didn't have were things that are called connectives. All right? And connectives are words we're going to use to connect two simple statements. So words like and or are very understood by our vocabulary. But words like if then and if and only if, those are very mathematical type connectives. Okay, you see those in higher level mathematics a lot. And or you see in math. If then statements are very, very common statements in mathematics. Okay, now again, like I said, we're not going to focus too much on the symbol stuff of this, but if you may see this symbol to denote and this one to denote or. I want you to notice the close connection between those symbols and our set union, set intersection symbols. They're basically just straight line versions of the set union and the set intersection. So where the intersection and the union were U's, here we have V's. Okay, kind of. Now an if-then statement is going to be denoted with an arrow, right? So one thing is causing the other. If this happens, then this will happen. Okay, A is causing B here. And if and only if goes both ways. There's arrows on both sides. So A causes B and also B causes A. All right. Now we're going to look at the idea of, the first connective we're going to look at is the or, because it's the most sort of misunderstood. In mathematics, we always use the inclusive or, but a lot of time, if you're just out and around or at a restaurant, they use the exclusive or. Okay. Now let's take a simple a statement with a connective, a compound statement. If I say I am 32 years old, or I have gray hair. Now the exclusive or would say you're either 32 or have gray hair, but you can't be both. All right, that's what the exclusive or is. So in our set theory, if this was A and B, exclusive or would say it could be A, it could be B, but it can't be in the intersection. All right. So it's kind of like saying, do you want corn or potatoes as a side? You can't have both. All right. The inclusive or well, that can include the intersection. It could be both. So if I am 32 years old and have gray hair, this statement would apply to me using the inclusive or. Okay? So notice that the inclusion includes the intersection. It includes both. Exclusive, well, we exclude the intersection. That's what it's really talking about. We exclude both. In mathematics, we always use the inclusive or. And that's kind of how we'd hoped it would be, because remember our symbols, inclusive or for a statement is this sharp one. Our union looks like kind of a soft, it's a U, looks like a softer inclusive or. All right, so these things match up, in other words. So anytime I'm talking about in this class, I am going to use the inclusive or for things. All right, now we do want to distinguish this, and if I give you the example, and it says, my cat is fat or lazy. Exclusive, or could the cat be fat and lazy? Well, if we were using the exclusive, no. Because remember, we exclude the intersection. We get rid of both things. The inclusive would allow the cat to be both fat and lazy. Now, a really important connective in mathematics is written as the if-then scenario. And what I mean by that is I'm saying if P is true, then Q is true. Remember, P and Q sometimes represent statements. Sometimes people draw those lowercase, other times uppercase. But we're saying that if we know P is true, then Q has to be true. So if the first part is true, then the second part has to be true. And a lot of sort of mathematical logic is written this way. And in particular, it's written so that, we lead from one result, which is P, to a different result that's Q. And then maybe you go to Q to an R, and then an R to an S. And so you go through step by step by step until you can say, we started with these assumptions, and we showed this last thing has to be true. Now, the if-then statements, what we're saying essentially is it's very similar to having the word all in here. So let's look at these examples. It says all healthy border collies have fur. Now, if I want to translate that to an if-then statement, what I'm saying is if the border collie is healthy, then it has fur. Okay? So all healthy border collies have fur can be translated to say if the border collie is healthy, then it has to have fur, or it has fur. I want you to translate this second statement into an if-then sentence. All right. So in the second statement, if the fat cat is named Charlie, then it is crazy. Oops. Ugh. Didn't draw that very well. And that should make sense. I hope that makes sense to you. This if-then type terminology. I should put a period there. Okay. Now, what we're saying with the if-then statement is that if I know healthy, then it's going to have fur, guaranteed. All right? If I know the name's Charlie, then it's guaranteed to be crazy. However, those statements are not reversible. Okay? So let's take another example. If a cat is brown, then the cat is crazy, is not the same statement as saying, if a cat is crazy, then the cat is brown. All right? So, in this case, brown is forcing us to be crazy. It's like saying, if we talked about the Venn diagram, well, if we know we're in B, then we're forced to be inside C. The other one is the opposite way. The other one is saying crazy is a subset of brown cats. So let's just take a look again. If this statement is true, let's assume this statement is true. That does not mean this one is true. Okay? If all of the B's are inside of C, that does not mean all the C's are inside of B. Okay. And that's, again, a very important thing, very important distinction that a lot of people will get wrong. A lot of people will say, well, this didn't work, or they'll try to reverse those statements. Okay? Now, notice that there's two parts to every if-then statement. Okay? There's the first part, and there's the second part. Okay? And just again, we'll do this in notation a bit. We have the if-then statement, P implies Q. If P, then Q happens. Okay? So, these two parts are called the necessary and sufficient parts. Okay? Be very careful about these. Sufficient and necessary are two important words. The necessary part is what's forced upon us if the original condition is met. All right? So in this case, and in all cases, the necessary part is going to be what gets forced upon us. It is necessarily true. So if P happens, then you're guaranteed to have Q. All right? So in this statement, if the cat is fat and named Charlie, then the cat is crazy. The necessary part is cat is crazy. All right? It's the cat is crazy part. All right? That's the second part. Now the sufficient part is going to be the first part. All right? Because it's sufficient, meaning it guarantees the consequence. If we know that P is true, then this consequence, then this Q is guaranteed over here. So if the P is true, then it's guaranteed that the Q is. So P is sufficient to cause Q. Right? So in our term, this is cat is fat and named Charlie. Fat and named Charlie. Then the cat is crazy. So the sufficient part is this first part. Okay? And just to write that down one more time, we have a P implying Q. If P, then Q. This is the sufficient, the first part. The necessary part is the second part. All right. So I want you guys to, in the following two statements, give me the necessary part and the sufficient part for the two statements. Necessary and sufficient. Push pause, give me those things, and then I'll state them as well. Now I want to say sometimes it's easier maybe to start with the first. So start with the sufficient part or the necessary part. It doesn't really matter to me. On the first one, I'll start with the sufficient part. The sufficient part is a person is not 48 inches tall. The necessary part is they cannot ride. By the way, if you were to rephrase this and say a person is not 48 inches tall is a sufficient, and then say a person cannot ride is a necessary, that's okay as well. So the point is, there are slightly different ways you can say this, or you can phrase almost every if-then statement you can phrase a little bit differently and get those. Now, in the second one, if the man's name is Greg, then the man is gorgeous. The necessary part is man is gorgeous. Sufficient part is man is named Greg. Now, I want to take a moment to say something about the if and only if statement. If you see the words if and only if, okay, it's meaning both. Essentially, A implies B, so if A, then B, and also the reverse of that, if B, then A. So it means both statements imply each other. All right? So it's kind of like having two if-then statements mashed together. So here's an example of an if and only if statement. A person is an unmarried male if and only if the person is a bachelor, right? So what that means is unmarried male guarantees that you're a bachelor, and bachelor guarantees you're an unmarried male. Like, same thing's true in the second one. The person is a friend if and only if the person is Emily. So, person being my friend implies that the person is Emily. And the person being Emily implies my friend. Okay? Now, as far as necessary and sufficient goes, notice that in this case, both statements, since both of them can be thought of as the front part of an if-then statement, and both of them can be thought of as the back part of an if-then statement, both P and Q are necessary and sufficient. Meaning, if you have P implies and is implied by Q, then obviously the P is necessary. And also the P is sufficient. So, right, we have this statement, which means both of these combined. So notice that this guy is necessary. So the P is necessary in the second one. The P is sufficient in the first one. The Q is necessary in the first one. Q is sufficient in the first one. So both P and Q are both necessary and sufficient on if and only the if statements. Okay.